My name is Anneli Mossberg. In this presentation we're going to cover the following. First, we're going to have a short introduction explaining the relationship between SystemModeler and Mathematica. We will then look at simulation-based analysis using the example of a DC motor. After that, we will see how models can be automatically designed from equations in Mathematica. Then we will look at model-based analysis centered around the model of a Lego Segway. Finally, we will look at an overview of what other powerful Mathematica functionality is relevant to modeling and analysis. Let's start by introducing how Mathematica and SystemModeler actually fit together. SystemModeler is a standalone software for modeling and simulation of dynamic systems. Mathematica is also a standalone software with extensive functionality in many areas. Connecting these two is the Mathematica package Wolfram SystemModeler link included with the SystemModeler. We load in the SystemModeler link package using needs WSM link, and we use the shortened name WSM link where WSM stands for Wolfram SystemModeler. Using this package, we can, for example, get a symbolic representation of a model, or get the model equations using WSM model data. Let's take a closer look at what we can do with this package, starting with simulation-based analysis. We're going to base our analysis in this section on a model of a 500-watt DC motor powered by a voltage source of 24 volts. Let's open the model of the DC motor in SystemModeler so we can see what the model looks like. To the left we have the electric parts of the DC motor, and to the right we model the mechanics with a weak axis using a rotational spring damper. We also apply a torque after a certain time to see how the motor responds to a load. Let's simulate this model using WSM Simulate. This function returns a WSM simulation data object containing all the simulation results. Of course, now that we have simulated, we want to see how the motor behaves. We use WSM plot to show the variables shaft.w and load.w, which represents the angular velocities of the axis. We can also look at the numeric value of any variable at any time we choose. For example, let's just retrieve the angular velocity of the load at time t equals 2. We can do that by accessing that variable from the simulation data object sim. A common thing to do with your model is to compare how it behaves for different parameter values. What happens when I change the damping in my weak axis? Let's find out. By using the option WSM parameter values, we can control the parameters of the simulation. In this case, we choose 3 different values for the damper. If we run this simulation, parallel kernels are automatically started, and simulation of the 3 different scenarios is done in parallel. The result we get from this simulation is of course a list of 3 simulation data objects. We can use this list of results in WSM plot to plot the same angular velocity as before and compare the result between the 3 simulations. The automatic plot legends tell us the variable names and which simulation the curve comes from. Now we know how to do multiple simulations with different parameter sets. This is a useful feature, but if we're looking for a more specific result, choosing the parameter values at random is pretty much a shot in the dark. A more structured way to go about this would be to find out which parameters would actually change the variable we are interested in the most. This is called sensitivity. So in our example, we want to know which parameters would affect the angular velocity the most when changed. In other words, which parameters is the variable most sensitive to. To do this, we first define a list of parameters in the model. Then we use WSM Simulate Sensitivity with this parameter list as a second argument. That will simulate the model and also calculate the sensitivity of the variables to each parameter in the list. Let's make a table of plots, where each plot shows the sensitivity of our angular velocity to one parameter. We again use WSM plot, this time with a new syntax for showing sensitivity. We give it a list with 3 elements: the variable, the parameter which we want to know the sensitivity to, and how much we want to vary the parameter. In this case, we want to show the load.w variable, the sensitivity to the parameter, and a variation of 0.2, or 20%. We also set the plot label to be the parameter name, as well as fix the plot range to more easily compare the plots. What we can see from the result is that two parameters don't actually affect our angular velocity at all. The blue line in the middle of each plot is the angular velocity, and the bounds around them show how much it would vary when varying the parameter by 20%. This is of course only true for smaller variations, but we can get a clear comparison of the parameter influence. We see that the resistance of the resistor and the transformation coefficient in the EMF component are the two variables that affect the result the most, as they have the largest bounds. Armed with this information, we can go on to the next step in our analysis. We have some measurement data from a physical version of this DC motor. What we want to do now is to find the parameters for our model so that it matches the measured data and the real-world DC motor. We start by importing our measured data and plot it together with the default setting of the parameters. We see that the measured data doesn't fit the simulation. We're now going to use the optimization functionality in Mathematica to find these parameters. To make the workflow easier to follow, we will do this in steps. Let's first set up some helper functions, variable value and gradient value. The function variable value simulates our model using the given parameter name and values and picks out the trajectory of our variable, load.w, from the results. The function gradient value does a similar thing but with sensitivity. What we get out from this is the variable's sensitivity to the parameter, which is the same thing as the partial derivative of the variable with respect to the parameter. In other words, the gradient in the parameter direction. Now we can use these functions together with Mathematica's optimization functions to find a better fit to the data. First, we vary the electromotoric force coefficient. We call findFit with our measurement data using our helper function to evaluate each iteration, varying the EMF coefficient value, starting from 1, using the time variable t, and finally using our second helper function, gradient value, for the gradient. Simulating with the results and plotting together with the data, we can see that the result is not so good. We see that the found fit has trouble reaching the same steady-state solution. As we saw earlier in the sensitivity analysis, the resistance and electromotoric force coefficients are the parameters that influence the results. So let's try varying the resistance instead. We do the same call to find fit, but for the parameter r.r instead. This call gives us the best guess Mathematica can come up with for our parameter p. If we now simulate with this parameter and show it in the same plots as the experimental data, it turns out that this is a really good estimate. Of course, you could also vary both parameters at the same time. This is left as an exercise. WSM Link also allows you to design and compose models directly in Mathematica. This makes it possible to automate model creation or quickly get started with modeling based on equations written in Mathematica. First, let's take a look at how to create models from equations. Here we have defined the differential equations for the Lotka-Volterra dynamic system, which models the dynamic behavior of a predator and a prey population. There are two different differential equations, one for the predator population and one for the prey population. We also specify the initial condition of the system. The parameters are the symbols that don't depend on time. Let's give them some values. Now we're ready to create the model using WSM create model. This would automatically translate these equations along with the initial conditions and parameter settings into a complete simulatable Modelica model and add it to the system. So it is immediately accessible in both Model Center and Simulation Center. We can also take a look at the Modelica text that was produced with WSM model data. Let's simulate and plot the populations over time. It is also possible to create Modelica models directly from the built-in system model objects in Mathematica, like transfer function and state space model. As we mentioned above, all created models immediately become available in Model Center. So let's connect the transfer function to an input in a new model. So let's create a new model, just name it something to your liking. Then we simply drag and drop the component onto the diagram view. Then we can connect it to, for instance, a simple clock source. So this shows how convenient and easy it is to actually compose models in Model Center. Once you've created models from equations or objects, you can use WSM connect components to build larger systems. This function builds a new Modelica model given a list of components and the connections between them. Let's build a simple electrical circuit. We specify the components and which class they are instances of using the element operator. Our circuit will have a resistor, an inductor, a voltage source, and a ground. Then we specify the connections between components. Here we need to know the names of the connector components inside the models. Then we create the new model simple circuit using WSM connect components. Let's verify that we didn't make a mistake building the model by simulating and plotting the behavior of the inductor. You can imagine that this functionality can be handy in all kinds of automation work. Let's give an example. Imagine you would like to create a lot of test models for your system to make sure it works as intended. The creation of these can be automated, and of course simulating and analyzing them as well. Let's test our simple circuit with lots of different voltage sources. We can find voltage sources in the standard library using WSM names. We'll remove the signal voltage from the list since it requires an additional input. Then we create a function to create one test model, given the voltage, source class, and an index, so we can directly use map indexed over the list of sources. Now we can create all test models with our function, and then we simulate them for 1 second and plot the current through the inductor for all results. As you have seen, we have, with a few lines of code, created an automated testing framework for our circuit. This can be generalized to, for instance, build variants of circuit models, and you can use Mathematica's combinatorial capabilities to calculate those variants. Now we have seen some examples of how to construct models, simulate and perform analyses based on the simulation result. Let's look at the next section, which covers analyses directly based on a model. For this purpose, we will use a model of a Segway built from components from a LEGO Mindstorms kit. We'll start by looking at the design model in Model Center. The model is built from custom components corresponding to the LEGO robot kit. We see the brick with the CPU, the motors, and the voltage control signals to the motors. Switching back to Mathematica, we now want to design a controller for this model. Our goal is to keep the Segway standing upright and to be able to steer it. It should also be robust enough to keep standing when we apply a force at the top of it, similar to nudging or pushing it with your hand. First, we need to get a representation of the model into Mathematica. We'll do this by calling WSM Linearize. This will give us a linear model of the Segway in the native Mathematica control systems format, a state space model. We call WSM Linearize with the argument initial values. These initial values are set so the robot starts in the upright position. This means that the model will be linearized in that position. So why do we need to linearize the model? Well, the robot is basically an inverted pendulum, which is a nonlinear model. Most control design theory is developed for linear systems, and so is this LQ controller that we will use in this example. We therefore approximate the nonlinear model with a linear model around a specific operating point, in this case the upright position of the robot. SystemModeler can provide both a numerical and a symbolic linearization of the model. In this case, we'll use a numeric representation. As you can see, the state space model is returned in a condensed form, which can be expanded. Now we'll remove some state variables using SystemModeler that we're not interested in. This gives us a smaller, more manageable system where we can see the angular velocities of the wheels, the angle of the robot, revolute.phi, and the angular velocity of the robot itself, as well as the currents controlling the motors. As inputs, we have the left and right motor voltages, and as the output, we have the speed of the right and left motor, as well as omega, the angular velocity of the robot. Now we define weight matrices for the control design. Our highest priority is to keep the Segway upright, so we set a really high weight on that variable. Using the system and the matrices, we can compute the gains for an LQ controller using the Mathematica control system function LQ regulator gains. We get a matrix of gains for our LQ controller. To verify the stability of the solution, we can connect the controller and compute the eigenvalues with the controller. We see that they all have negative real parts, meaning that the system is stable. With this promising result, we're ready to save the result into a model and simulate it. For this purpose, we have a model with a controller. Let's take a look at it in Model Center. This blue component is the model of the Segway we saw before. We've added a feedback loop with an LQ component. We've also added some disturbances that push the robot in different directions, as well as two steering signals, one for each wheel. Going back to Mathematica, we use the function WSMSetValues to set the computer control parameter values in the model. We can verify that our controller actually works by simulating the model using the control parameters. For that, we start Simulation Center to also get the automatically generated 3D animation. We see the progress indicator showing the build process. When the build is finished, the simulation will start immediately. The build is now finished and the simulation will start automatically. Once the simulation is finished, just click the Animate button to get a 3D animation of a Lego Segway, staying upright and withstanding pushes. We can zoom in to see it a little bit more closely, and then press play. The green arrow on top of the Segway illustrates the pushes we apply to it. And as you can see, the controller can handle these disturbances, and so the Lego Segway is able to maintain its upright position. I have now shown you a few areas of functionality which relate to modeling with SystemModeler and Mathematica, but there are many more. And here we can see an overview of some of the functionality of Mathematica and how it relates to SystemModeler. The arrows show some of the things you can do with your SystemModeler models with Mathematica. We saw several examples of simulations of models controlled from Mathematica. We used optimization functionality in Mathematica to calibrate our model to fit experimental data. You can use the powerful symbolic equation handling in Mathematica to prototype custom components or models. Here we changed the switching times for different gears in an automatic gearbox. We also analyzed our DC motor model in several different ways. You can use Mathematica for both control design, or use the powerful symbolic graphics language to create custom visualizations, as shown here. The interactivity features of Mathematica, such as Manipulate and Animate, allows interactive explorations of your models and their behavior. These are just some of the ways Mathematica and SystemModeler can be used to solve a wide range of problems, and Mathematica is full of more features, algorithms, and functionality for use with SystemModeler.